All right, so we are ready to go. So before we begin today's class, I just want to point out a few resources just so that you're aware that they're on Canvas. So in the Canvas modules, you will have, of course, you'll be familiar with the Access Online resources here. So that's where you can get all of your resources for the course. But new stuff that I added, just in case you haven't seen it yet. So links to my YouTube channel where I post these recorded lectures is now available directly through Canvas. So the first link here will take you to the course playlist, including previous semesters of this course. So if you do ever feel the need to work ahead, you can use that as a resource, absolutely. And then individual links to the classes so far, and I'll be posting this week's classes here as well. Just so that you're aware, depending on your browser, this will either take you directly to the YouTube video or it will take you to a page that says it cannot load it in Canvas and then give you an external link above that window. So you're either 2 clicks away or 1 click away from watching these videos, so just to be so you're aware of that resource. And then also here, I have an online office hour booking app that I use. So office hours, just to be clear, are walk-in friendly, no appointment necessary whatsoever. So anytime you just kind of feel the need, feel free to come by on office hour. But if for whatever reason you feel the need to have a guaranteed time, you can book office hours, and you can book them in half-hour or 1-hour installments. And there's a link there that will take you to my online booking solution. And then there's also availability of Friday online Zoom meetings if required. So if none of the office hours really work for you, we can always set up a Zoom meeting on Friday, and you would also book that through that link there. All right, so just want to make sure everybody was aware of that. And now we're ready for today's class. So what we're going to be doing today is we are going to finish up our look at attention. We didn't quite get through everything that we wanted to do. We had one CogLab left over. So we're going to finish that off. We're going to finish off spatial queuing, CogLab number 2. And just to be crystal clear, spatial queuing CogLab number 2 will be on the first exam. So I thought we would get it done yesterday, and that would be the end of what we were covering for the first exam. This first few minutes of today's class is the last little bit that we need to cover before we begin on the new material, which is perception. All right, so spatial queuing CogLab. In this CogLab, we had 3 conditions. There was a neutral condition, there was a valid condition, and there was an invalid condition. And it was all about how quickly you could detect a particular target. So you were staring at a screen, and then a target would pop up, and you had to indicate when you saw the target, and then measure your response time. So the 3 conditions are neutral. In the neutral condition, there was no arrow telling you where the target was going to appear. In the valid condition and invalid conditions, there were arrows. And in the valid condition, the stimulus appeared where the arrow was pointing. So if the arrow pointed to the left, your target would appear on the left. If the arrow was pointing to the right, your target would appear at the right. And in the invalid condition, the stimulus appeared where the arrow did not point. So the invalid condition was lying to you. The arrow would point to the right, and the stimulus would come over here to the left, and the arrow would point to the left, and the stimulus would pop up on the right. And your task was to respond as quickly as possible to that target, to that red square. So as soon as you saw it, you hit your key, and your reaction time was recorded. And it would either, again, appear to the left or to the right of a fixation point. And during each trial, you were instructed, and this is one of the important features, you were instructed to fixate on that center point. You were instructed to fixate either on the center cross or on the arrow, and not move your eyes from where you were looking, but you could move your attention. So you could take your covert attention and move it to somewhere else. So if you're looking at somebody, you can always try to pay attention to people in your periphery. It's not a natural thing to do, but you can move your attention away from where you're looking, and that is your covert attention. That you are allowed to move, eyes you are not allowed to move. And then just to kind of keep you on your toes, the valid condition, the stimulus appeared where the arrow pointed, but only 80% of the time. So it was valid, but only 80% valid. And then the invalid condition was invalid, but only it only occurred 20% of the time. Sorry, I misspoke. The valid condition occurred 80% of the time. So it was always truthful, but the valid condition occurred 80% of the time. The invalid condition, always lying, but it occurred 20% of the time. And the reason they did this is so that you would not disregard the arrow. So 80% of the time, the arrow was telling you the right direction. So in general, it's a good idea to listen to the arrow, but every once in a while, 1 out of every 5 trials, it was a bad idea to listen to the arrow. All right, so let's take a look to refresh your memory what this looked like. So the neutral condition, you would see a fixation point in the center. You were supposed to look at that. It would change to a flat line, and then at some point after that, a target would appear in either the left or the right, and you would hit detected it as soon as that target appeared, and it would record how quickly you were able to detect that target. In the valid condition, which occurred 80% of the time when there was an arrow, you would have your fixation point, you would see an arrow, the arrow would be pointing to one side, and in the valid condition, that's where the target would occur. So you could move your covert attention, you were supposed to keep your eyes in the same place, you could move your covert attention, and the target would be where you moved your attention. And then finally, in the invalid condition, it was the opposite. You would see the fixation point, you would see an arrow pointing in one direction, and the target would appear on the other side of the screen. So if you moved your covert attention over here, there would not be a target there, and you would have to detect it on the other side. And this only happened, again, 1 in 5 times when there was an arrow. So it was to your advantage to listen to the arrow, not disregard it, and follow the arrow where it pointed. All right, so what happened? What were the results of this this signaling of where your attention should be? So here we have the 3 different conditions. So we got the neutral condition, no arrow. Valid condition, arrow points to where the target eventually ends up. Invalid condition, arrow points to the other side. And then we have reaction time here in milliseconds. And notice first off that all the data is going to go between 310 to 380 milliseconds. So we're talking less than 5%. We're talking about 5% of a second. So it's really quick. But these really quick reaction times have big implications for cognition. So cognition operates at the speed of milliseconds. Small little differences in milliseconds can make huge differences in cognition, which can make huge differences in behavior. So what are we looking at here? In the neutral condition, that's how fast you were at detecting the target. So this is kind of your baseline condition, because in this case, you had no information about where the target is. So about 360 milliseconds, about 1/3 of a second, that's how fast you are, just in general. That's how fast the average person is at just doing this particular task. When we take a look at the invalid condition where the arrow was lying to you, you took more time to make it to the target. So there was an additional time penalty for moving your attention to the wrong area and then having to bring it back across the screen to where the target was. And this is further given evidence for in the valid condition, where you were much faster than the neutral condition. So we're faster in the valid condition. So when you move your attention to where the target is and then the target appears there, you are very quick to respond. But when you move your attention away from where the target is in the invalid condition, then you are very slow to respond, indicating that you have to take your attention from that incorrect location and drag it all the way over to the correct location before you can say, yes, I processed that area, I detected it, there's that target in the other area. All right, so any questions about the data, the results for this one? All right. So why are you faster in the valid condition and slower in the invalid condition? And what does this mean about how we move our attention? So any speculations on this? It's been a long week, I'm assuming. All right, so I'll be sympathetic. So why are you faster in the valid condition and slower in the invalid condition? What was moving? If you do this correctly, your eyes weren't moving when you necessarily moved your attention in these conditions. What was moving was your attention. So when the arrow pointed in the valid condition to the target, before the target appeared, you were able, even if you were fixated on that center position, you were able to covertly move your attention, right? Just the same way that you could be staring at somebody and yet keeping your peripheral vision on the door to see if somebody else comes in. You can keep that attention, you can keep your eyes focused on the center, but move your covert attention to where the target is going to be. And then once that target appears, your covert attention is there, you've selected that area to process, and you're very quick at making that detection. You're very fast at making that detection because your attention is already there. On the other hand, in the invalid condition, the arrow points one way, you move your attention, you're waiting for the target, and then all of a sudden it appears in the other end of the screen. And notice that what this implies is that once it appears at the other end of the screen, you know that something has appeared, but you don't know what exactly has appeared. So you need that time to take your attention and drag it over to that other area, process that area, say, oh, there it is, there's a red square, I've detected it, and that's that response there. So this gap between these two, 330 milliseconds approximately for the valid, 370, 380 approximately for the invalid, that difference of 50 milliseconds, that measures how long it takes you to drag your attention from one side of the screen to the other side of the screen. Because when you're right there at the correct side, that's how fast you are. But if you have to go from the correct side to the incorrect side, this is literally how long it takes your attention to make it all the way over to that other side. And you can see that extremely closely, the neutral condition is right about in the middle. So if you are staying in the middle, as soon as you see a target on the other side, you have to go to those other sides. You're halfway between, and it's just about halfway between those two reaction times. All right, so this is in the lab. So once again, in the valid condition, if your attention is here and the target appears here, your attention is already there, ready to process, don't have to move it. On the invalid condition, if your attention is here, whoops, I can't do spatial rotation. If your attention is here and you're ready to process this location and then you notice something over here, you have to move your attention to that other location, and that takes that extra time. All right, so we have an effect here. We have different reaction times. Just as a sort of final review of endogenous and exogenous, what is driving the effect in these conditions? So there's a number of different effects in these conditions. So let's start with the arrow. So the arrow pointing you in one direction or pointing you in the other direction, and then you move your attention to the position that's pointed to. Is that endogenous attention from within, or is it exogenous attention from without, stimulus-driven attention? Mm-hmm.
So would it be endogenous because we're inside, like, kind of fixating on the same shape, and each other, like the square arrow?
Yes, so it is endogenous, you're right about that. It comes from inside, it's goal-directed, and it's because of that rule. It's because of that goal of finding the square, and the arrow is supposed to help you find the square. So what the rule is this arrow is going to point to the square. It's not exogenous because there's nothing about an arrow that makes you look to where the arrow is pointing, other than our long history of working with arrows. There's nothing in the stimulus itself. If you showed an arrow to somebody who had never seen an arrow before and it was pointing this way, their eyes wouldn't immediately go like this, right? There's nothing biological about arrows pointing our attention somewhere else. It's goal-directed. We know how arrows work, and we were told in the instructions the arrow is going to point to the location. So when we move our attention to where the arrow is pointed, that's goal-directed. That is a goal-directed form of attention that's endogenous, coming from within. On the other hand, when we see the square, or when we detect the square, all of a sudden, wherever our attention is, it'll whip over to where the square is. Now, is that endogenous or is that exogenous? And we'll say primarily, which one is it? Any guesses? Probably the other one, since I have the two options. All right, so that's exogenous, because there's something about the square that is grabbing your attention, right? You're over here looking at blank space, and all of a sudden something over here is going on, and your attention just naturally will go over here to that other side. So the fact that it's a target and you're looking for it is not primarily what's drawing your attention. The flash, the something new, that red square on a black background, that's the stimulus itself that is pulling your attention. And another way to think about this is that if you skipped the instructions on this CogLab and you just opened it up and said, I'm just going to do the CogLab without reading the instructions, don't do that. But if you did, when that red square popped up, you would still look at it. Even without instructions, your attention would still go to that red square. Because it's red, because it's a square, that's exogenous stimulus control from the outside moving your attention. All right, so that was in the lab. Now we're going to take a look at an application of this. And we are actually very fortunate here at IUSB. We have one of the world leaders in the study of the psychology of magic. So Dr. Ladd is one of the best in the world on the study of the psychology of magic, which is a really emerging area of psychology. So we're going to take a look at how this idea of endogenous and exogenous attention can be used in the service of magic behavior.
Ladies and gentlemen, Penn and Teller! Oh, thank you again, and welcome back to the show. First of all, I want to congratulate you on, you guys are the longest running headlining act in Las Vegas.
In history. Not just now, the longest running headliner in history in Las Vegas.
Congratulations, that's just
We
amazing.
just signed for another 4 years, so until 2022.
At the Rio.
We intend to die in office.
Oh man, I can't believe I love that. Now let's talk about the 5th season, Penn and Teller Fool Us. Explain the show to people if they haven't seen the show. It's a good premise.
Greatest position in the world, and we're in the 5th season, it really is the world, people from all over. They come on, they do a magic trick that they think can fool us, and if they can fool us, they come out and play with us in Vegas at our theater, the conveniently named Penn and Teller Theater, and if they don't, they go away crying.
Yeah, exactly.
And, this season, we're also bringing back, which is not thrilling us, we're bringing back people who fooled us before, fan favorites who come back on and try to fool us again.
Now you always bring a cool thing or do something amazing as some type of illusion or trick, and so you're doing something tonight. I never know what it is.
Yeah, we didn't let you in on the rehearsal.
No, I never know. All right, good.
What
do I do?
Yes. You can watch it right there.
Okay.
You know, there's a word, misdirection, that's used by lay people a lot. It's a magic term. It's a term of art. And the way lay people use it is wrong. Because lay people often use it as a synonym for distraction. Like, hey, look over there, do something sneaky here, and then you look back and the trick's done. That doesn't fool anyone. Mm-hmm. The way we use the word misdirection is kind of a curating of attention, giving the audience a story they can tell themselves that lets them not really know they were distracted. We're going to do a trick right now using misdirection. I'm going to tell you what it is. The trick is the vanishing chicken. There's a chicken in there, we're going to make it disappear. Now, when I say give you a story to tell yourself, it's not some jive-ass story like this is Clucky McCluckface and this is the chicken coop rocket ship to Mars. No, a real story, which is it's a vanishing chicken, I told you.
Yes.
You know we're Penn and Teller. You know we do magic tricks. So as soon as I cover up this chicken, you're telling yourself what you're going to do. You're telling yourself a story. You're making yourself a promise. Because you're promising yourself right now that at no time will you allow your attention.
Oh my goodness.
Misdirection. Now, Jimmy, I want to see how well this works. Get the house lights up. Let me see people. Yeah, just want to see. Show of hands. How many of you saw the gorilla with the symbols? Jimmy, everyone. It's a goddamn gorilla with symbols. Jimmy, all of you.
Yes, yeah.
Now, subset of that. How many of you saw Teller walk out here, pop the chicken, and split? That's almost everyone too. Now, here's where the misdirection comes in. How many of you, during all of that, saw sneak the gorilla into the cage? I never saw that because that's misdirection.
Oh my gosh!
That's different assets.
Are you kidding me? Oh my gosh!
All right, so that is a very, very nice example of exogenous attention, endogenous attention, and also the importance of stories and the stories that we tell ourselves. So the story that we're telling ourselves was that was a trick about a disappearing chicken, and in reality it was a trick about a appearing gorilla. But importantly for our examples in here, talking about attention, it used a combination of endogenous and exogenous attention. So the endogenous attention, the goal-directed attention, was what Penn, I believe, is the one that talks. He was saying that you make yourself a promise. You say, I'm going to pay attention to that box, right? I'm going to figure out what's going on, and I'm going to direct my attention towards that box. That's endogenous attention from within, because there's nothing really that special about the box. Once the gorilla comes out, that's exogenous attention, right? Like Penn said, it's a gorilla, right? Everybody noticed the gorilla. You don't have to be told to pay attention to the gorilla. That's exogenous. It just grabs your attention. In fact, you have to be told to put your attention back on the box. You have to move it. That's endogenous, moving it back to the box. And when you put everything together, you can sneak a gorilla into a box somehow. Or maybe the gorilla was there the whole time. I don't know how they do it. But again, it's basic, fundamental, millisecond effects of attention that can be built into something as just weird as that. All right, so any questions on attention before we wrap up our look at it? Okay, so that was the official end of where exam number one is going to, what exam number one is going to cover. So make that note in your notes. From here on out, this is exam number 2 territory. So when you're studying, save perception for study time for exam number 2. But do make sure that you do review spatial cueing, and of course, endogenous and exogenous attention will definitely be on exam number 1. All right, so perception, chapter 3. So now we're moving into one of the other, the next sort of classic, fundamental, iconic areas of cognitive psychology, which is perception. So this is my predominant area that I experiment in psychology. So we're going to take a look at some of the important work that was done here. And we'll start off, once again, basic as you can do, with what is perception. So we can all do perception. We all know we have 5 senses. Turns out we have way more than that. But what exactly is perception? What is it? So we need to define it just like we defined attention to make sure that we're talking about what we think we're talking about. Next thing we're going to take a look at is 2 forms of processing that occurs in attention, being top-down and bottom-up processing. We're going to take a look then at experience-dependent plasticity, which is a fancy way of saying when you perceive something, it changes the way you look at things. So the mere perception of objects, the mere perception of your world is not a passive activity. You're active in your perception of the world, and then the world itself folds back on your perception and changes the way that you see things. So the more whenever you look at something, you are different for having looked at it, and part of that has to do with experience-dependent plasticity, and we'll see a very interesting study that took a look at whether faces, this very important visual stimulus, whether they have a special processing mechanism that is dedicated to faces, or is it a general processing mechanism that is mostly dedicated for faces just because we look at so many faces and they're so very important. And we'll take a look at the very famous Greebles study by Gauthier et al. All right, so what is perception? So perception is experiences that result from the stimulation of the senses. So that is the basic definition. It's experiences that you have, cognitions that you have, because of your senses being stimulated. And that's the key portion there, senses being stimulated. So if there is a rabbit in the real world, and that rabbit, or if there is a picture of a rabbit on the screen, light is being reflected off of that rabbit. That light is hitting your eyes. It is stimulating your senses. And then any experience that you have of brown furriness because of that, that is perception, right? It's an experience that came from stimulation of your senses. If, on the other hand, there's no stimulation of your senses, then that's not perception, that's a hallucination. So if the rabbit doesn't exist, but you still see the rabbit, it's termed a hallucination, and that's a completely different area of cognitive psychology. So we're going to focus in on perception, and it's very important to realize that perception is your experience based on the stimulation from the external reality. It's your experience based on the stimulation of your senses. And because it's your experience of the outside world, your perception can be correct. And most oftentimes, it is correct. So if there is a rabbit out in the real world, and you see a rabbit out in the real world, you're usually correct, right? If you see a chair in the classroom, you are usually correct in the fact that there is a chair in the classroom. And you can test it out by sitting down, and you'll find that the chair is actually real. So your perception can be correct. And thank goodness most oftentimes it is correct, but it's important to realize that your perception can also be incorrect. And this is most easily shown by taking a look at illusions. So let's take a look at this Mueller-Lyer illusion, very famous illusion here. So we'll zoom in on it, and how many people perceive, we'll do a show of hands, how many people perceive that this line here in the A section is longer than this line here in the B section? So how many people perceive A is longer than B? How many people perceive B is longer than A? How many people perceive that as being the same? Okay, so if you perceived it as B longer than A, or if you perceived it as being the same, you should book an appointment with your eye doctor, because nobody sees this in any way except A being longer than B. So this example here is to prove the point that perception is not the external reality. Perception is your experience of the external reality. And when you take a look at this illusion, this looks to be longer than this. And we have all seen this one probably before. We've all taken out the ruler and measured it. And if I was to ask you, are these lines actually the same size? Most of you would be able to say, yeah, I've seen this one before. They are the same size. But do they look to be the same size? Is your perception of them the same size? No, it's not. If your visual system is working properly, you will see this line as being longer than this line over here. So to give you another example where perception is different from the external reality, where our experiences, because that's what perception is, our experiences from stimulation from our senses, we have this anamorphic picture over here. And this is a picture of the Peanuts gang walking across the Abbey Road intersection from the Beatles album. And it looks like cartoon drawings. It looks like somebody took cardboard cutouts and painted them to look like the Peanuts characters, and then stood them upright on this road, and then took a photograph of them. So that's what it looks like. That's what your perception of this external reality is. In this case, though, your perception is completely incorrect because that's an anamorphic painting, and there's no cardboard cutouts, and this is what is actually painted on the surface of the street. And what happens is that your mind takes this stimulation, and then the experience you get, the perception you get, is of this up here. So if we zoom in on this, and let's flip it, we'll rotate it so that you can see Marcy in relation to what was drawn. So this is your perception. This is what's actually out there. This is the external reality. But the stimulation on your senses that comes from this chalk on the ground makes your mind see this as an upright figure. And the correspondence, you can see that there, the color right there is the color right there. Her hand is that hand right there. Her shoe is that little splotch of paint right there. And then if we zoom in to where her head is, notice it gets larger the further away it goes, and that's part of what tricks your mind into thinking that it's upright. But there's her bangs right there, there's her nose right there. And all of that done together and knowing how your visual system works, the stimulation that is being caused by these, this external reality of this warped image on the ground makes you perceive, it gives you the experience of upright figures walking across Abbey Road. All right, so always keep that in mind. Most often, our perception matches external reality, and that's why it's so often easy to mistake your perception for being what is actually out there. But our perception is actually our experience of what's out there, and that experience most often is true, but oftentimes is incorrect. And as psychologists, the incorrect is extremely interesting because when somebody gets something incorrect, that is usually when you have the best chance of figuring out what are they actually doing. So the errors in perception are one of our greatest tools to figure out how is your perceptual system working, because there are a number of different ways to do things correctly, but there's usually only one way to do something specifically wrong, and that's why we oftentimes use illusions as perceptual scientists. All right, next idea in perception. So we mentioned that perception arises from a stimulation of the senses. It's an experience from stimulation of your senses. But that's not the only place that information comes from in perception. Information for perception comes from the stimulus itself, but it can also be combined with other information that you've already stored in your mind, other representations that you already have in your mind, and that is the key difference between bottom-up versus top-down processing. So bottom-up processing, that is the information, or the idea that information for perception comes from the stimulus itself. That the stimulus itself is the source of the information and is the predominant place of the information that is used in your eventual experience, your eventual perception. So the stimulus, in this case, is considered the bottom. So bottom up means you start at the bottom, which is the stimulus, and your processing moves on up until you have your experience. And that's bottom-up perception. And an example of bottom-up perception, we can see in this picture right here. So most everybody is able to perceive that there are five distinct, let me back that up. Most people are able to perceive that there are 5 distinct animals in this picture. And even if you didn't know what a horse was, if this was the first time you were ever seeing horses, even if you've never experienced the color brown before, you would still be able to take a look at this picture and say, there are 5 things there. There are 5 separate entities there. And that's bottom-up processing. There is information straight from the stimulus. So for example, the abrupt change here from brown to black, that indicates that this edge is 2 separate horses. The gradual change here indicates that these edges here are part of the same horse. So that's an example. We won't go into too much detail, but just from the stimulus itself, you can tell a lot about this picture. You can perceive what is coming, what is in this picture, what your perception is, just from the information coming up from the stimulus. All right, so that was bottom-up processing. The opposite of that is top-down processing. And this is when information for processing comes from higher-level general knowledge. So this higher-level knowledge is considered the top. So in bottom-up processing, you got the stimulus down here, and the stimulus works its way up until you have your perceptual experience. In top-down processing, after the stimulus works its way up to your perceptual experience, you still have almost no idea what you're looking at until your top-down processing comes and further processes that information. So top-down processing is the idea that the important part of perception is the previous knowledge, the other representations that you can bring down from previous experiences to interpret that stimulus. So the important part is what comes from the top, what comes from your higher cognitive general knowledge. So to give you an example of this, we have this illusion here. So this is a very famous illusion. So how many people have seen this before? Okay, cool. We got some people that haven't. So if you haven't seen this before, hands up if your experience is of a elderly woman. All right, hands up if your experience is of a younger woman. Okay, so this is an example of an ambiguous stimulus. So from the bottom up, some of you have processed this information and you have said, all right, I see an elderly woman. From the bottom up, some of you have processed this information and say, I see a younger woman. And it's possible in both of these cases to change your perception by putting top-down knowledge on top of it, by putting top-down processing, information from higher cognitive processes on this. So if you see an elderly woman here, then you can force yourself to see a younger woman by mapping this orientation onto this image here. So if this is your eyelash or her eyelash, that's the eyelash. That's the nose, that's the nose. She's looking away, she's looking away. There's your jawline, there's your jawline right there. There's your ear right there. She's wearing a choker, she's wearing a choker as well. After that top-down information, how many people can see the younger woman? Okay, so that's an example of top-down processing. You've changed your perception based on higher level general knowledge. On the other hand, if you had already seen the young woman, you can change it and see the elderly woman as well. So for the elderly woman, this is the unambiguous elderly woman. That's her nose right there. That's her nose right there. That's a bag under her eye. There's your bag under her eye. This is also a bag under her eye with her eyelash right there. This is a mouth. There's your mouth right there. This is a chin. There's your chin right there. So now that general information, that top-down information has been put up there, how many people can see the elderly woman? Okay. So this is one of the kind of key demonstrations to show that top-down processing has to be a part of perception, because this stimulus can be seen two ways. You can experience this stimulus two ways. You can force yourself to see it as a young woman. You can force yourself to see it as an elderly woman. And the stimulus does not change. So the fact that you can have two separate experiences means that it cannot be completely determined by the stimulus itself. It has to come somewhat from top-down processing as well. All right, so we got bottom-up processing, we got top-down processing. And it's important to know that both of these are a factor in perception. And it's not as important today as it was previously, but you will always encounter arguments and controversies and different camps butting heads in perception based on how much of perception is top-down and how much of it is bottom-up. So what is the more important portion of perception? Is it mostly bottom-up, where we don't really need a lot of top-down processing to explain how we perceive things? We should focus on the stimulus. We should focus on what's coming into the eye. Or, on the other hand, is it mostly top-down, right? Is the stimulus itself extremely ambiguous so that you actually are unable to make decisions? Is it an elderly woman? Is it a younger woman? I can't really tell until you get that top-down processing, and that's what kind of makes sense of your work. So there's been a lot of debate, a lot of controversy on this over the years. So, and really what they're asking is, how do these two interact? How are the two of them put together, and how do they influence each other? And which one kind of has the greater share or the greater importance in making that final experience? So I'll give you one last example to give you to show you the power of top-down and bottom-up processing. So this is another example of perception. So I'll zoom in on this. So this is a very, very, very famous painting. This is by an artist called Held. And you are looking at something that you have seen a million times before. Does anybody know what they're looking at? Hands up if you think you know what you're looking at. All right, we got one person maybe. Okay, I guarantee you you've seen this object before. All right, so we've had this stimulus up here for about 30 seconds right now, and we have one person that maybe has perceived what the object actually is. So that's bottom-up processing. Right now, all you got to go on is bottom-up processing. I have told you very little that would allow you to do any top-down processing on this image here. I've given you the stimulus, and I've said, what do you see? And most of you have not been able to see what it is. If I give you the title of this painting, I can then activate your top-down processing. So the title of this painting is called The Big N. Who can see the N right now? A lot more people, right? So we went from pure bottom-up processing to virtually nobody being able to see or recognize what this object is, which I assume you've all seen before, hopefully. But then as soon as I said, oh, it's the big N, all of a sudden that top-down information, people's hands went up. They're like, oh, now I see it. This is the N. So if you were writing this N, you would start here, you would go up, you would go down, and you would go back up there. So it's a very heavy font. It's a very thick N. In fact, it obscures everything in the background except that little triangle down there and that big triangle up there. But it is an N, and once you know it's the big N, then all of a sudden that top-down processing gives you that almost aha moment where you're like, oh, there it is. It's the big N, of course. And interestingly, we're not going to address this, but interestingly, you will remember this for the rest of your lives. This is the last time you're going to be confused by the big N. So I don't know what museum this is in, but if you ever visited it, it doesn't matter if it's 5 years from now, 10 years from now, or 20 years from now. Our visual system works in that way where if you pop in there, you'll look at it and be like, oh, right, big N. And you'll remember this. So it's not even that, it's that groundbreaking of a flashbulb moment, but there's just something about these illusions where you just you don't get to see them twice for a lot of them. All right. So that was a very clear example of the importance of top-down processing. People did not see the big N until we said, hey, it's a big N. That is almost exclusively, I would argue, top-down processing. You got the stimulus, don't know what it is until somebody says big N, and then it changes your perception. All of a sudden you're like, oh my gosh, yes. This is figure, this is ground, this is the front, that's the back. I get it now, I can see what's out there. Let's take a look at another example. Take a look at another example. There we go. All right. So this is another image. And how many people, let's start off with the easy one. How many people know cognitively, know rationally that this pencil is not broken? Okay, good. Now, how many people perceive this pencil as not being continuous, perceive it as actually being broken? Okay, good. So that is another example of the difference between reality and perception. We know the pencil is straight, but we perceive it as broken. And in this case, this is a very interesting example of predominantly bottom-up processing, because you could bring in somebody from our physics department and they could give you a 1-hour lecture about the propagation of light and how it propagates in straight waves. They could tell you about the propagation of light through a medium. So we have the medium of water, we have the medium of air, we got the medium of glass. They could tell you about the different diffractions that occur based on the wavelengths, based on the length of the waves. I think longer ones get diffracted more, or shorter ones get diffracted more. One of them gets diffracted more. We could spend an hour explaining it. And at the end of that hour, you could be completely an expert on diffraction of light. 100% an expert on diffraction of light. And I could ask you then to take a look at this, and you would still say, it looks bent. So all of that top-down information, all of that knowledge, that general knowledge about how light works and how diffraction works, doesn't do anything, in this case, to correct your perception. I tell you that the painting is a big N, all of a sudden it's like, oh, now I see it. I tell you that this pencil is straight, doesn't matter. You still cannot force your perception to see it as straight. So this is a great example of the contribution of bottom-up processing. All right, so just so that we have we'll do one more example. So what I want everybody to do, we're going to show a picture here. And just like before, we had a picture of horses. And I eventually was able to see that there were 5 horses. So we're going to try that again with a new picture. I'll zoom in on it. It's going to be this picture here. And what I'd like you to do is count the horses. How many horses are there in this painting? All right, so how many people see at least 1 horse? How many people see at least 2? 3? Do I hear 4? Do I hear 5? 6? Okay, good. So you found all 5. And nobody found 6. Someone was like, is there another hidden horse? All right, so there's 1 horse here. So this is 1 horse face. That's another horse face. So that's 2. There's 3. There's 4. And then there's 5. And notice that this one was probably a little bit effortful. So unlike the previous one, the previous example of bottom-up processing where I said, even if you don't know what horses are, you can very easily say, well, there's 5 things there, there's 5 entities there. You didn't need top-down processing for that. For this one, you needed top-down processing. So there's a lot of bottom-up processing going there. But you also, because of the nature of this picture, needed to start asking yourself, what do I know about horses? Right? What information can I bring to this about horses? Oh, look, here's a hoof. I know horses have hooves. I'm going to follow that up, and there's that other horse, right? I know that because the rocks look so much like horses, you need to bring information about what horses are like and what they look like in order to correctly identify what is a horse and what is not a horse. Because bottom up, this area looks a lot like this area, but you need to bring in that top-down processing in order to arrive at the perception that there actually are 5 horses in this case. All right, so that would be a very nice example of kind of both processes working together. So in the perception literature, if you go into perception as your area of psychology, you will run across a lot of studies showing that bottom-up processing is definitely the most important. Most of our perception is bottom-up. And then you'll find a lot of studies that show counterexamples, and they go, no. Most of our perception is top-down. This was a big issue because for a long time, bottom-up processing was thought to be impossible, logically impossible. So I believe it was Hume, the philosopher, came up with an argument that perception is logically impossible without previous knowledge. So the world out there is 3D. Your retina has a flat screen. That compresses everything. You have no information for depth. Perception of depth is impossible. So there was literally debates about whether or not bottom-up processing is impossible. So what we're going to take a look now to kind of end this is we'll take a look at the 3 stimuli that we have here. So we had one that was mostly top-down. We had one that was not affected by top-down processing, mostly bottom-up. And then we have this one, which is the combination of the two. And the question is why are some of these more top-down and why are other ones more bottom-up? Any ideas looking at those different stimuli there? Okay, so the suggestion was, could it be the need for context? And that is absolutely part of the answer. So here you have virtually no context whatsoever. When I say, what is this thing? You have no context, you have no idea about what's going on here. There's very little context information to draw upon. Here, when you see this, you can draw upon more sort of contextual information. So you can kind of perceive that these are rocks, that this is, snow. And even if you don't know what rocks and snow are, you know that this area is different from this area. So there's a little bit more that you can bring into it. And then here we have a ton of contextual information, so that it gives you a bunch of information that you can draw on. So why would that make this more bottom up and this more top down? If this has more sort of context and this has less context, why would that be the case that one would be bottom up and one would be top down? I'll give you a hint. It has to do with the fact that cognition is information processing.
Similar to why we read left to right?
I wouldn't say it's similar to why we read left to right necessarily. No, I wouldn't. Yeah, I think that's more of a practice aspect of perception. Yep.
Is it like a need to understand?
It's from a need to understand things. And what do we do? What do we access? What's the basic thing we access when we're trying to understand something? Previous knowledge is one possibility, but more generally, what is previous knowledge? I'm looking for a specific information. I basically spoiled it. I'm looking for a specific word. And if you caught the first 4 letters of the word there, what are we looking for? Not inexperience. What are we processing in cognition? What's the basic thing? We are blank processing systems. We are information processing systems. So when there is, and that's the key difference here. So you touched on it with contextual information, for sure. You touched on it with general knowledge, for sure. In order to achieve perception, we need information. We need some sort of information, and it has to come from somewhere. And you will notice that when things are very clearly mostly driven by bottom-up processes, like this one over here. Once again, I could explain the diffraction of light to you for months. We could have an entire course on the propagation of light. You would still see that as a broken pencil or a bent pencil. That is because so much information is coming from the stimulus. This is a detailed photograph. We have enough information coming from the bottom up from the stimulus that the top-down processing has a negligible effect. In fact, I would argue it has no effect, right? Because you cannot make that that stick look straight. On the other hand, you take a look at this stimulus over here, it really has way much less information, right? You look at all the different colors and all the texture changes here. There's almost nothing here. So your mind still needs information in order to achieve perception. It still needs to process something to have the experience. But the stimulus in this case is not giving you anything. The stimulus is very sparse, very little information. So you need something from the top down. You need it from a different source. So when I say, oh, it's a big N, then all of a sudden you're like, oh, now I have the experience, now I have the perception. And this one is somewhere in between, because it's in between in terms of information. So it's got slightly less information than this picture over here. It's got more information than the big N over here. And that's why in this case, if you couldn't see all 5 horses, and I pointed out one of the faces, then you would be able to see it. So it's a lot of bottom up, but also a lot of top down in that one over here. So remember that as you go forward in psychology, if you take future courses in perception, you will come up on this top down versus bottom up debate once again. And most of the time when there is a debate, if people are like, well, it's mostly bottom up, it's because they're dealing with stimuli that look like this. And if other people are like, no, it's mostly top down, it's because they're dealing with stimuli that look like that. You need enough information in order to process the stimulus, process the information to have your perception. All right, any questions on that? Comments? All right, so the last thing we're going to do today, we're going to be able to I'll introduce this idea. We'll see how far we go, and we'll probably wrap it up a week from today, because remember, next class, exam, and then we'll set this up and see how far we can get. So one of the kind of interesting things about the way that our brain works, the way that our brain implements our mind. So we've been dealing mostly with mind. Now we're going to switch gears just a little bit and talk about how maybe the brain achieves the implementation of your mind. One of the very interesting things that came about from work on perception is this idea of experience-dependent plasticity. And this is where your brain, your actual brain structure, can be changed by experience. So if you were to map out your brain, the parts of your brain that are dedicated to certain areas, the parts of your brain that process certain information, you can change that depending upon practice, depending upon experience. So experience-dependent plasticity is why when you pick up a musical instrument like a violin for the first time, you're horrible, but then after years of practice, all of a sudden, you can play the violin. Your physical brain has actually changed, dedicating more of your brain to your hand because of this experience-dependent plasticity. So one of the areas that came under question in neuropsychology in terms of what is this area for? So one of the big questions in neuropsychology is, what is each area of the brain for? What does each area of the brain do? How does it, what is its function? And one area that was identified is called the fusiform face area, and that is this area right there. So it's in your human temporal lobe, so it's on the side. And this is an area, and you can tell by the name, it's called the fusiform face area. This is an area that is believed to be specialized to respond to faces. So it seems to be an area that is specifically dedicated to processing faces in the human brain. So the question that they had is, we found this area that seems to only respond to human faces. The question is this area just for faces? Were faces important enough evolutionarily that our brains developed a specific area just for processing faces? So vision is important, and our brain has a specific area just for processing vision. Moving is important. Our brain has a specific area just for processing movement. Our face is so important that our brain has a specific area just for processing faces. That's one possibility. Another possibility could be that this is an example of experience-dependent plasticity, meaning that we are so trained at recognizing faces, detecting faces, processing faces, interpreting faces, that we have actually changed our brain to have an area that responds to faces. So just the same way that the violinist will have an area of their motor cortex expand to represent more of their hand, did this fusiform area turn into an area that processes faces because it's in general for highly trained stimuli, and we just happen to you see faces very often. And this is another one that might not be apparent until you point it out. If you count how often you look at faces and how often you process faces, it is astounding how common a stimulus it is. So think about just looking around the room today, right? Faces after faces after faces after faces. Getting ready in the morning, you got a mirror, face, 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 face. Any movie that you watch, if your movie contains people, you see face after face after face. We see a lot of faces. We see faces a lot. So, it could be that just because we see this stimulus so often, and it's important in terms of social interactions, maybe it's just for trained stimuli. So to answer this, is it special or is it trained? Gauthier et al. Did a study with Greebles. And what they did is they wanted to see if humans were given another stimulus and they practiced on that stimulus, could we get the fusiform face area to process that stimulus? So if you were to practice identifying something over and over and over again, could you get so practiced at it that your fusiform face area would become specialized for processing that as well? So if your fusiform face area changed because of your training on these Greebles, then that would indicate that it's just for trained stimuli, and we're just happen to train ourselves on faces a lot. On the other hand, if you could train yourself on these Greebles and your fusiform face area stayed dedicated towards faces, that would be an indication that it's specialized for faces and nothing else. So I was talking about Greebles. I haven't shown you one yet. So that is a Greeble. So that's one example of a Greeble. That's another example of a Greeble. Here we got another Greeble. And here we have the entire population of Greebles. All the different types of Greebles. And what they did in this study is they would show their subjects these different Greebles. And you would have to identify what their gender was. So their gender, we have all of these Greebles over here. They are glips. We have all these Greebles over here. They are flocks, right? So first thing you needed to do, is it a glip or is it a flock? And then you have to identify which family it's in. So is it in the Panaz family? Is it in the Omit family? Is it a Gaz? Is it a Barks? Is it a Tasto? Which one of those families is it? So you would start off this experiment, and they would show you this, and they would be like, what is that? And you'd be like, is that a flock Tazo? And they'd give you feedback. They'd be like, no. That's a glib Gaz. Like, okay. And then they would show you this one, and you would get it wrong. And then they would show you this one, and you would get it wrong. And what they found is that this was actually something humans could learn. So eventually they would show you a Greeble, and you would look at it and go like, oh yeah, that's a flick Tazo. And you'd be right. You'd be like, yes, this is definitely a glip Gaz. And you would be correct again. So the closest I think we've ever come to this in popular culture, if you've ever met somebody who can name all the Pokemons and identify the evolutionary stage of each Pokemon, is basically they've done what these people have done in this experiment. Just through repetition and through experience, they were able to take a look at one of these and directly identify family and gender. So what did they do? Well, what they did is they took a look at the fusiform face area responses before this training on Greebles and after the training on Greebles. And we're going to see the results, and then this is where we're going to end it once we take a look at those. And we'll see what it really means in a week from today. But before training, when they had them in that fMRI, when they had them in the, I think it was an fMRI, when they had them in the brain scan, before they were training, they measured what are their responses to Greebles in that fusiform face area. Those are the results right there. So let's take a look at both of those in turn. So first we have the brain scan here. And what you can see is right there, that is your fusiform face area. that is its responses to faces. And all of the colored areas, those are the places that are responding greatly in your brain when you see a face. And then all the gray areas, those are the ones that do not respond to faces. So that's how you read this diagram here. And this is your area of the brain that is your fusiform face area. And you can see, you show somebody faces, and that area of the brain gets lit up. That's what identified it as a possible processor of faces. When you show somebody Greebles, no activation. That area is silent. So before training, faces lit up the fusiform face area. Greebles did not light up the fusiform face area. And if we take a look at the graphs of that, once again, they measured the fusiform face area response. Higher bars mean higher responses. And before training, there was your responses to faces in your fusiform face area. There was your responses to Greebles in your fusiform face area. Basically showing what they already knew. This is specialized faces activate the fusiform face area. Importantly though, what happened after training? So after training, it was a completely different story. After training, there was large responses to Greebles in the fusiform face area. So this is before training right here. Blue bar is your response to Greebles. That's after training. All right, so once again, before training, very little response to Greebles. After training, fusiform face area lighting up when people saw a Greeble. So once you could name the gender and the family, once that Greeble popped up and you're like, oh yeah, that's a flake tazo, this is what your fusiform face area was doing. So it was comparable to faces. So once again, before training, there's the activation for faces, there's the activation for Greebles. After training, there's your activation for faces, and there's your activation for Greebles. So not as much yet, but you got to understand this is an experiment that took weeks, not the lifetime of experience with faces that people have. Yep.
Why did the bar for faces go down?
So why did the bars for faces go down? That is probably because of the way that the fusiform face area responses are measured. I don't know the exact operational definitions of how they calculated, 10, 20, 30, 40, but they wouldn't go down because of the experience, but probably relatively they were approximately the same at that point. That would be my answer, but I would have to take a look at that a little bit more. But that was a good catch. But importantly for us, they're almost comparable now in terms of their responses. So that's what they found. Training on the Greebles activated your fusiform face area. And what we're going to do next time, so that's where we're going to end today. Next time we meet, exam number 1, but then a week from today, we're going to take a look at what this actually means. So what I would like you to do after exam number 1, try to remember this for Wednesday after exam number 1, take a look at this and start trying to think of reasons why this would still not indicate that your face is just for trained stimuli. Because it really looks like, well, they trained Greebles over here, so the fusiform face area is for trained stimuli. Can you still argue that it is for faces? If so, why? Can you find other examples of why it would be for trained stimuli? If so, why? That's what we're going to pick up on a week from today. So that's it for what I wanted to cover today. Next class, exam number 1, all the way up to attention. A week from today, we'll pick it up on Greebles. Other than that, have a great weekend.